Shading both tails. Two-tailed test. So I'm trying to get my two t-crits. You know me, I always use the yellow chalk for the t-crits. These would be the same values except one will be negative, one will be positive. Now this is my favorite part. How am I going to get these? Because everything in there are degrees of freedom for this problem. Okay. So with what we call, this is called a two-sample t-test. All right. Back in the day, everyone, before we had technology this advanced with these calculators, I mean, like the TID4 couldn't do this. What we did was we used the sample size of the group that was the smallest. So here they're both 18, so we'd use the sample size of 18. And then the degrees of freedom would be 18 minus 1, which is what? 17. We actually use, because we have our calculators, we use a degrees of freedom formula. Now, the calculator will produce it for us. Does anyone want to see this thing? I'll write it on the board if anyone wants to see this formula, and then I'll erase it, okay? This is not on the formula sheet, because it's not a very, smooth, it's not just a quick formula. But this is the formula that we're going to use with our calculator to find the degrees of freedom. It's equal to, I'll write on the board, this is on page 559, by the way. But I wanted everyone to see this thing. I just didn't want to leave it on the board all day, because it's not like you're going to go and enter this. We'll let the technology in it. Because it's a lot of computations. It's very tedious, cumbersome. Do all this squared all over. Squared. So if someone in here was using let's say, I'm thinking a scientific calculator. Well, then I would recommend to them to just use sample size 18 and use degrees of freedom 17. But this is what's going to get computed. N sub 2 squared all over n sub 2 minus 1. I just wanted to see where this is coming from. Well, there's group 1, there's group 2. Standard deviation of group 1, standard deviation of group 2, sample size of group 1, sample size of group 2. You know all this stuff, right? But we're going to let the what? Let the calculator produce this for us. We just enter all this in L1 and L2, let it compute for us,
So
okay?
degrees of freedom is not 17 here?
I know, because so for a two-sample t-test, you could use that, but if we have the technology available to us, we should use this little formula here, because it's stored into the calculator and it will compute it. But guess what they've done? Let's say a class, students don't have a what? Calculate like this to use our Microsoft Excel to store that in some cell in Microsoft Excel. Then they'll just use the sample size of the two groups that's smaller. So if this had like 51 students and this one had 60 students, we could say sample size equals 51, degrees of freedom equals 50. And that'd be a safe route to go. It'd be close to the t-crit we're going to get anyway. It wouldn't be a big difference. It wouldn't be a big difference. But we'll let the calculator do this. So we're going to get a funny degrees of freedom off our calculator. Cool. All right, so where are we going on this thing? And we're about to get these t-crits. We can find out where it is, but we're going to use the calculator to get the what? Degrees of freedom. So, let's go on here. Boom. Here, just clear the screen, go to Stat, go to Tests. Last class we used number 2. We're using two-sample t-test. This is a two-sample t-test. This is what you always use for independent samples. Two-sample t-test. All right, so hit number 4. Now, are we doing stats or are we doing data? We have data. And when we have data, so we're going to hit data. List 1, L1. List 2, L2. Frequency of 1, just keep it 1, because that means one column. Frequency 2, just one column. Which one of these do I want?
The first one.
Yeah. Then we get to this pooled question. Everyone, never pool with this test. Sound good? We won't pool. And I'll talk about that. we use what's called a Welch's t-test. And Welch's t-test, we won't pool. You go, well, what's pooling? If you ever wanted to pool, we'd have to have knowledge about the two populations. We'd have to have knowledge that the variances of the both populations were roughly the same. These two groups. We don't have knowledge of that. Okay? So we're not going to pool. We'll never pool with this. Sound good? So just hit no. Say, I'm never going to pool. And then we'll hit calculate. But this should produce that degrees of freedom for us. It's going to be a funny number. I wonder, what's the degrees of freedom? Let's see. It's not a neat number. It's a 31.85333, right? All right, so I'm going to write that down. I'm going to put it down here. Degrees of freedom, I can erase this formula now, equals 31.85. All right. Which is roughly 32. Produced from this. Thank you very much. Calculator. You saved me a ton of time, right? Can I erase this thing? I do want to point out, it will always compute that for you. But yeah, Art, if someone didn't have this computer or calculator, then they could have just used, okay, sample size 18, degrees of freedom 17. They've been close enough anyway. So, I've got that. Now, I want to show my t-crits. So I'm going to use the t-table. I'm going to use the t-table to get this. Degrees of freedom, 31.85. What's the closest on this table to a 31.85?
32, so 30.
There's a 30. So I'm going to use 30. And then what's the alpha level?
0.025.
And we go, excellent. And so this is 0.05, right? But when I'm trying to get my t-crit off this table, it's two tails, isn't it? So how much is in that tail? 0.025. 0.05 divided by 2. How much, what area is in this tail?
Same.
It's, yeah, 2.5% each tail. So when I do this, I'm going to look at 0.025, match it up with degrees of freedom 30. Okay? That's what I'm going to do with this. Now, who's got a really cool updated calculator and you got the inverse t button? All right, they're just going to enter this. Inverse t, 0.025, and you can even write 31.85. Because that's the degrees of freedom. That's what they'll do. I'm going to use this, and when I got a at 30, 0.025, what comes up?
2.042.
2.042. So I got my secrets. 2.042. This is negative 2.042. So put me right off that 2, everyone. It's right off these little 2's here. Right around here. Meow. Make sure this is lined up a little bit better. There you go. I'm going to just off this negative 2 mark. This is right after that little 2. All right. Now let's go back, look at our technology, our calculator. What is the sample test statistic, which is produced from this, everyone? Sample test statistic comes from here. And what do we get?
2.37.
2.37. So, I'm going to plot that. It's called the classical approach. 2.378. I'll put 2.38. Let's plot that in here. Where is that?
To the right.
It's not right there. There it is. Is it in the yellow zone?
Yep, we reject the null.
Is it in the critical region?
Yep.
Reject null. And we are rejecting the null. And there is evidence suggesting that these are different. All right? Using these different manuals. But I'll complete all the writing now. What's the p-value?
0.023. 0.024 we can use.
P-value 0.024. So I'm just going to quickly talk about this p-value. Because the p-value
It's low.
is lower than the
Alpha level.
alpha level. What are we doing about the hoe?
Reject.
Reject the hoe. We reject the null. Conclusion? I'll write it down, I'm going to state the conclusion, but there is evidence suggesting that the
Has
mean of the visual learners is different from the mean of the textual learners. See, there's really a difference here. You can go back with the screen and you want to know, well, who scored better? If you're just curious, who scored better? We didn't look who was better or worse. We want to see if it's different. You can tell that the mean of the what? Visual manual scored better. Cool. Hey, before I state my conclusion, I just wanted to do a confidence interval. Because we can do a confidence interval because it's two tails. I just want to do a confidence interval on this. And then I'll state my conclusion. So my confidence interval is, I'll hit the lights. And this is awesome because when I go in here to just look at a confidence interval, I'll just come over here and go like this. Stat, test. We just did a 2-sample t-test. Guess what I'm looking for? A 2-sample what? T-interval. And the calculator will keep all those same numbers there, right? So it'll be really, really easy to do this. I go to 2-sample t-interval. I just want to look at this. Same stuff. It's from the data. What confidence level should I put because of the level of significance here with 2.5% each tail? What's in the middle? 95%? Yeah, so I'm going to use 95% here. And here's the idea. If we don't get a 0 in this interval, that gives us further evidence that we're rejecting a null. So does this interval, we don't pull. Does this interval contain a 0? 1.21, and what's the upper number? Alright. 1.2 to 15.8. I'll just call it the 1 decimal place. Evan, this interval does not contain what? We are 95% confident that the difference in the population means is between 1.2 and what? 15.8, and I want to emphasize, and does not include what number?
0.
Yeah. It doesn't include a 0 difference, meaning no difference. So there is some difference. We are very confident that there's a difference in the means. We're 95% confident that the difference is somewhere between these two means. So I'm now going to state my conclusion. I just wanted to make a interpretation of the confidence interval too. We are 95% confident that, you go what? That the difference in the two population means, the difference of them, the difference is between these numbers. And the difference didn't include a what?
0.
0. So now I'll state my conclusion. Conclusion! I'll wait till the end to do this. But we knew it a long time ago. We looked at that p-value. We knew this. There is evidence suggesting mu of visual is not equal to mu of textual. Yeah? That cool? Everyone, great job with this. We'll do another one, but this is my favorite part of this class. You go, why? Believe it or not, you may not think of it now. You may find yourself doing this. But it'll be in your field of expertise, right? Well, I'm going to be a dental hygienist. Or, no, okay, I'm going to be a nurse. I'm going to do this, and you're working on your master's degree, etc. All of a sudden, I got to do some research. I gotta write up a thesis, I need to actually go out and do some kind of experiment like this and put people in two different groups, you might find yourself doing this. And you'll say, all right, I'm gonna do all this stuff, I'm gonna do it randomly, just like I learned in statistics. I'll put the two and break up these two groups in a random manner, completely randomized design, and come to the end to see what you got. All right. Now, if you do have sample sizes less than 30, then you'd want to check those normal probability plots. And it wouldn't be hard to get access to software like Minicap to help you produce those. Okay? All right, super job. Let's do another one. Any questions on this? Super job. So we rejected the null. We rejected the null. This next problem, everyone, you may like this one better because we don't have to enter all the data. They're just going to give us the what? They're going to give us the statistics. They're going to give us the sample mean for visual. They're going to give us the sample mean for textual and stuff like that, right? You saw in the calculator, we found it through there. So they're going to be given to you. Can I erase? All right, wipe it out, wipe it out. All right. This time, everyone, we won't do the confidence interval. But we'll set it up. We'll verify requirements. Same level significance. But all this will be given to us. All right. So I'll get these L1s and L2s out of here, everyone. This problem, this is on page 562. This is number 8. All right. Researchers conducted a randomized, double-blind study to measure the effects of the drug olanzapine on patients diagnosed with bipolar disorder. Okay. So a total of 115 patients